How's that? I'll just talk kind of loud too. Thank you everyone for coming to our PDR this year. Decent turnout, I'd say. We'll get started right away because we have quite a bit of content to get through. Just to give you a quick idea of how this will go, we'll run through some introductions, talk a little bit about how our team is organized and managed and laid out and all that. Then go right into our designs, starting with structures, going into propulsion, avionics, recovery, payload, SARP in that order. Finish off with some acknowledgments and leave time at the end for questions, but we'll also stop between each subsystem for questions. And we will ask that you guys hold off on questions until the end of the subsystem section. So real quick, as I mentioned, I'm Jess Grant, the Chief Engineer of SARP this year. We have Kevin Chow, our Project Manager, Avionics Lead, Sabrina Tong, Recovery Lead, Aaron Goldfogel, Jimmy Reagan, Propulsion Lead, Austin Cassera, Structures Lead, and James as our Payload Lead. Brief history of the team. We started off in 2009 as the first time that UW entered a sounding rocket into the Intercollegiate Rocket Engineering Competition. And in 2012 is officially known as SARP with only around 10 members. They placed first at IREC. Fast forwarding a little bit to 2017, the team had second place at IREC with another hybrid launch. And then this last summer in 2018, we placed first in our category of 30,000 foot Apogee hybrid to liquid motor at the competition. And actually, we'll move on to Kevin now to go over some of our team management. Outside.
So is this on? Is it on? Okay. Project more? You got it, Jimmy. So this year we have over 190 members, which obviously really exploded for the past couple years. And because of that, we can't do a simple organization structure. We have to divide into more teams. Currently, right now, we have, again, Jess, Chief Engineer. I'm the Project Manager. And we have all the same teams with structures, payload. Does anyone have a laser pointer? Jimmy? There it is. So we have with structures, payload, propulsion, recovery, avionics. And we also have our business counterpart teams, which this one is for finance and operations. This one's marketing. And each one has their own respective project leads for structures, payload, propulsion. And avionics and recovery is kind of the same team this year. So we kind of combined them to one category or subsection. Business team is small enough so then that each individual members are their own team leads, essentially. So for this year, for team objectives, team requirements is dictated by IREC, such as reaching a target altitude of 30,000 feet, limited to a Class 2 amateur rocket. Also, fully student research and develop hybrid motor, full tracking systems, CubeSat scientific payload of 8.8 pounds, also within the normal CubeSat units of either 1U, 2U, or 3Us of 10 by 10 by 10 per U. Also have a minimum stability margin of 1.5 calibers. The overall team goals is to have a fully wireless launch operations, and this year we're doing a 7.9 rocket diameter. Again, more dimensions is about 13.25 feet with 7.9 inches in diameter, weight for dry weight of 120 pounds, and then wet weight of 170 pounds. For wet weight, it's basically the nitrous and your solid fuel that's added on top of the dry weight. And we also have a target thrust of 1,200 pound force. So currently, this is a brief overview of team schedule, a general team schedule. Right now, we're in week 10 of fall, which is for PDR and some senior capstone integration. So we're basically on time here. Manufacturing will be continuing on through winter till halfway through, and then more testing and integration throughout all of winter. This CDR may or may not happen at this week, depending on how more following designs go, and also test launch windows, and then for IREC prep after that for later spring quarter. This year, since UW ends the year a week later, after week 10 is basically we're heading down IREC. So we don't have that week to do more IREC prep work. So now on to structures with Austin Cassera.
Sounds like the microphone's working. All right. So I'm Austin Casera. I'm the structures lead this year. So just a quick overview of some of the requirements that we have. From IREC, they basically just want us to make sure that we fully analyze the structure and make sure there's not going to be any surprises in terms of failures, things like that. COPV is a joint project between Propulsion and structures that's going to have a kind of a special case scenario because COPVs just started becoming used in IREC the last year. So some of our own goals for this year, we set for the structures team a minimum factor of safety of 2 for all of our components. We also, of course, want to integrate effectively with all the other teams, no problems. Just makes it easier when we get to assembly. And then some of our research and development projects this year that are big, the composite overwrap pressure vessel, COPV, that will actually be mentioned in Jimmy's propulsion slides later, and the composite couplers, another big R&D project that we're working on for weight reduction. So just a quick design overview of the rocket. Almost everything you see on the outside of the rocket is structures. So we have the nose cone, the payload coupler. We got the parachute inside the upper body tube. Both the drogue and the main chute are stored in there. We have the recovery coupler, which houses the oxidizer vent valve, the main body tube, which covers the oxidizer tank, and then there's the actuated valve bay in between there. Then we have the fins mounted on the fin can and the tail cone at the end. So just to give you an idea of where all these parts are. So start off, we got the nose cone. The purpose of the nose cone is just to minimize drag, and we chose a 47-inch von Karman curve based on the mostly subsonic, some transonic flight that we'll be undergoing. This was decided using iterative open rocket simulations. Open Rocket is an open source rocket simulation software we use. The nose cone will be made of fiberglass prepreg laid up into a high density foam female mold. The female mold allows us to have a nice outer surface finish for aerodynamics. The nose cone tip traditionally is machined out of aluminum and epoxied and bolted on the top of the nose cone. However, this year we would also like to integrate a pitot tube into that nose cone tip. The way we plan on integrating this is using the titanium printer, the titanium 3D printer in the mechanical engineering department. So we're working on things for that, but we still have to work out dimensions and taking into account if we go supersonic, what that's going to look like with the pitot tube. So the nose cone also integrates with the plasma payload. You're going to hear more about that in the payload presentation by James. And the nose cone connects to the payload coupler with 4 radial bolts. Again, this is kind of one of those plots that we compared different shapes of the nose cones with, and this is for the von Karman curve, which came out with the lowest drag. We're also, as part of integration with payload, there's going to be some holes in the rocket to hold on their electrodes, and also, or in the nose cone, there will be some bolt holes to hold on their electrodes, and then also very small holes for their wires for temperature sensors. We don't anticipate these holes to be an issue for structural purposes, but we are going to run some FEA. We just haven't done that yet. No issues anticipated there. As far as testing goes for the nose cone, we are going to take the material after we cure it and expose it to extremely high temperatures. In the case that for some reason the plasma does heat up the surface of the nose cone a lot, which again we don't anticipate too much, but we want to make sure that the nose cone doesn't catch on fire. So we're going to do testing for that. And we'll do wind tunnel tests to verify that the geometry we chose is the optimal choice. So the payload coupler right underneath the nose cone houses the payload. It has those mounting bars in there for it. It also has CO2 canisters for the nose cone ejection, what separates the nose cone and allows the parachutes to come out. And it also has the hard point for the drogue chute on the aft side of the bulkhead. So the bulkhead and the sleeves will be machined from aluminum and welded together. The welding will be done professionally. That goes for all of our welding. And the payload mounting bars will be made out of carbon fiber just to make them a little bit lighter. And there's going to be a 1/2-inch eye bolt for the mounting point for the drogue chute. And there are 2 current CO2 canister configurations. There's perpendicular, which is on the right, and there's parallel, which is on the left. So we've run analysis for both of those cases. This parallel configuration has more holes, a little bit smaller,
and the perpendicular has 2 larger holes for those CO2 canisters. Both check out above our minimum factor of safety of 2, and the perpendicular one actually shows up a little bit better. And the highest load that we have here is the drogue parachute load, which is 360 pound force. That's what this is done for, using von Mises failure criterion. So our airframes, we have 3 tubes that we make. They're all carbon fiber, and they are the aerodynamic surface of our rocket for the main tube, and they also hold a lot of parts together. So the top one that you saw was the parachute bay, and then we have the Oxidizer Tank shroud, which will be load-bearing this year. And the fin can, depending on geometry, will be made the same way, and we'll talk about that later. The material we use is Toray T700S fiber with a 2510 resin system. It's pretty strong, works really well. We've used it in the years past. We use an aluminum mandrel, just a big circular tube that we hand lay these tubes up on. That method is practice and proven. So, and all of these tubes are connected to all the interfacing components with bolts. So, as far as an analysis for the tubes go, we have done some FEA with composite ply stack pattern in there, and we're working on developing that more, but most of our analysis has come from classical laminate theory. So as part of our composites course, we've developed a code that analyzes various stack patterns, and we've used that to show that actually moving away from our traditional 0, 90, 0, plus 45, minus 45 stack patterns. So those numbers correspond to the angle of the fiber relative to the 0-degree axis of the rocket. And the direction of the fibers is what takes the load mostly. So by moving away from those plus minus 45, since these tubes don't really have a lot of torsional load, we were actually able to get a higher factor of safety. So the upper body tube sees mostly axial loads, so we move those fibers to the plus minus 20 direction. And for the main body tube, this is something that we're still working on. You'll notice that we have this internal pressure factor of 1,000 psi. And part of that is with the COPV, there's going to be a bonding surface that you'll see in those slides later between the COPV and the inside of the Ox tank shroud. And it's not a complete contact surface throughout the whole length, but we're not exactly sure how to translate that internal pressure, which is really 800, but we're not exactly sure how to translate that internal pressure, and we're still working on that FEA to determine how that loading will translate to the tube. So to be conservative, we threw that in there, and we still come out above our minimum factor safety of 2. All of our bolts, quarter-inch bolts, grade 8 steel, and they all have a decent factor of safety. If we only have 4 bolts, and for some cases we'll have more than that, so we should be fine. FEA shows that the holes in the tubes will be fine too at those points. Recovery coupler. So this has the main parachute hard point. So there's a large force there after the deployment of the parachutes. The bulkhead and cage for this are also machined from aluminum and welded together professionally. We will have 3D printed doors, which have worked great the last 2 years. And the unsupported column length, which we'll get into on the next slide, that's 8 inches for this current design. The eye bolt is 5/8 inch diameter, so it's pretty hefty. So last year, the mode of failure was a buckling in the recovery coupler. So we wanted to make sure that we're safe in buckling this year. We used Euler's critical load in buckling theory to calculate a factor of safety of 9.4. This L is that unsupported column length we talked about in the last slide. And K, because this is one solid part, we technically have fixed ends, so we're putting a value of 0.5 in there. E is elastic modulus. I is minimum moment of inertia for the minimum moments of inertia for the column. And then to verify that with FEA, we calculated similarly successful factors of safety for all the components in the different loads. Show a little bit lower in compression, but that's actually our max stress there is right up in those corners, and so we would expect the material to yield there first before the column buckles, which probably would then result in the column buckling as well. But again, we have that large factor of safety there. We don't anticipate getting to that point. So one of those R&D projects I mentioned, composite recovery couplers. This is, again, just a weight savings thing, very R&D at this point. We would basically be replacing that cage of the recovery coupler with carbon fiber, manufacturing a tube the same way we have in the past, and then adding stiffeners on those columns. One consideration that we're still working on is making a bulkhead that takes the 1,800 pound force of the parachute load, which I forgot to mention on that last slide, is giving us some difficulty. So the backup plan is to still have an aluminum bulkhead, and the conversion from the aluminum cage to the composite cage will still give us a lighter part. This would require a lot of mechanical testing, some destructive testing, and then proof testing before we would ever put it on the rocket. The fins, this is our major stability, our major control surface. And we have 4 geometries that we've chosen, which you'll see on the next slide. We, again, use OpenRocket to determine these geometries. There are 2 options, basically, for the fin can, which is just the tube that the fins are connected to. There's a cylindrical fin can, and there's also area rule. Area rule is if you take a look at the cross-sectional area of the rocket, along the length of the rocket, you want to keep it completely constant, and if you do that, your drag over flight will be significantly less than if you were to not keep it constant. And so when you get to the fins and you add that extra area, you actually have to choke down the diameter of the fin can and to keep that area constant. We'll be doing wind tunnel testing to verify which fin geometry is best, and in addition, we'll be throwing the 2 different types of fin cans, a couple different nose cone geometries to verify that the one we chose was right, and a couple tail cones, which we'll get to later, all in there. And CFD and FEA are both being worked on for the fins right now. Currently, this Delta 2 shape is showing the lowest amount of drag and the highest apogee for the rocket. Stability is something we also have to consider, so we're taking a look into this. These are preliminary graphs right now, so as we get better data, better simulations, these numbers could change slightly. That arrow's a little off, but it's supposed to be pointing towards D2, highest number. Manufacturing the fins, we have a honeycomb or foam core, and it's overwrapped with carbon fiber. The 2 options essentially will come down to making a fin can, whether it be cylindrical or with the area rule with a slight waist, and bolting those fins onto the can. It's something that we used last year that worked pretty well. If you notice, there's some aluminum inserts inside this foam core that's from last year, and then they bolt into the tube like that. So there are 2 methods of making the area rule fin can, either this male mold option or this female mold option. You can't really see the area rule curvature that goes into the depth of the page here. But these are 2 options that we're looking into, and we've talked with some of the shop masters over in ME and with some of the professors here, and we seem pretty confident with that. So tail cones, the last part we have, the purpose is just to reduce drag again, and also made of carbon fiber on a foam mold. Aluminum will work too. Foam's probably what we'll end up using though. And this integrates with the nozzle, so it's pretty much constrained to the nozzle geometry. This transition length is just the axial length from this point to that point. And so in this analysis that we have here, we show that as that transition length increases, that is, as the angle decreases, that we have better performance, which is no surprise. However, increasing the length of that tail cone would imply that we also need to increase the length of the nozzle, which comes into inefficiency issues. And so those are conversations that need to be had, but most likely will just be constrained to the nozzle geometry. And we do show that having even a small tail cone is better than having no tail cone, both for an unthrottled and throttled case. And you'll hear more about the throttling of the oxidizer from Jimmy. This is some very preliminary CFD. These are actually using old fin geometries that need to be changed now. But that is something that we're working on, and so we'll see some further analysis there. Moving forward, we will have all of our analysis complete just about a week or 2 after school starts next quarter, and all of our testing that would result in design changes will certainly be done by February, early February. And CDR is scheduled there for everyone. Manufacturing, now this includes some backup components that we want to manufacture, and that'll all be done by the end of winter quarter. So proof testing would be after we create those parts before they fly. We do want to do proof testing all of our parts, just a 1.5 times expected load in the Instron machine or something for compressive or tensile loads, whatever that may be. And then we hope to do some ultrasonic inspection on our carbon fiber parts, but we have to find someone that can do that. And that's my cue. And it is Jimmy's turn. What? Oh, yeah, questions. Okay. Do we have any questions on what? Oh. Sneak peek at the propulsion system. All right. Any questions on structures things? Nothing. Anything coming in from the computer? Kiefer saying anything? Okay. Well, we'll give them a second, I guess. But yeah, Ricardo. I'm sure that that's probably an idea that we, what? Oh, sorry, okay. He asked if the cross-sectional area of the fin is something that we're looking at in case there's a huge side gust, and I guess that, pushes the rocket in a moment. I think, Hannah, that's probably something that your team has looked at, but.
Yeah, right now we're trying to. Right now we're trying to decide if so we have how far there is.
Yeah, so Hannah was basically saying that depending on the option between the regular fin can and the area rule fin can, right, in the steady level flight, we're limited in our ability to choke that diameter of the fin can based on the combustion chamber that's inside of it. And so those areas that we'd be looking at and how that would interact with some gusts could change potentially down the road. So it is on the list to check. Why do we move away from the swept fins? Okay, that's a great question. So if you look here, yeah, so you'll see that these fins go past the tail cone. So they look really cool, but as the rocket comes down in a parachute, it lands directly on the fins and they break. So in an effort to not remake the fins every time we want to do a launch, we are moving the fins to not extend past the tail cone. Any other questions? How do we plan to attach titanium tip? Titanium tip, that's what referring to the nose cone. We plan on epoxying it mostly, and that should hold fine, but we will be looking into potential bolting designs, such as the, last year there was a piece of all thread that hooked into a platform that kind of sucked up into the inner side of the nose cone and held the nose cone tip on. And that's something that we're also looking into, because there will be some electronics that need to be hooked up to the pitot tube in order to collect data. And so that would be a good opportunity for us to mount those there. No? So of course the wind tunnel, the question was, will wind tunnel testing be done with a full-scale model or with a subscale model? It will not be with the full-scale model. It's a pretty large rocket to throw in the wind tunnel. However, the test model is larger than last year's. Last year's was about this long, and there are a lot of interactions between the test stand and the model in that instance. And so we are moving up to a significantly larger test rocket that's 5 feet long. Yeah. So a lot bigger, but no, not full scale. Any more? I don't know if the simulations have been run on that. Oh yeah, sorry. The question was, what performance increase do we expect from using the area rule fin can as opposed to the cylindrical fin can?
So biggest reduction for drag.
We're looking for a drag reduction primarily.
So hopefully a couple out of our
But have you looked at those numbers at all?
No.
Yeah. No. Okay. I didn't think so. So we're mostly looking at a drag reduction there, and most trade studies show that there is a significant decrease in drag when you go to the area rule. However, given our constraints with the combustion chamber inside, we still have yet to run that analysis for our rocket and see how much of a gain that would be. But we do anticipate there to be a slight increase. We just have to decide after we run that analysis whether it's going to be worth it for our team or not. Any more online? Any more in the audience? Why are factors of safety so high on this rocket? So our highest factor of safety is certainly in our carbon fiber tubes, and those have always been really high. You notice there's a factor of safety of 62 on the upper body tube. That component is extremely thin, very light, and once you reduce, it's 10 plies in our carbon fiber tubes. After you shrink from 10 plies, you start running into just the rigidity of the tube is not very high. And for the purposes of our student club, a couple plies of carbon fiber is not a huge weight savings one way or another, so we keep the 10 plies. For couplers, we're actually still looking at weight reductions from last year, even with our increased factors of safety. So part of the factors of safety for the recovery coupler, we want those to be really high because that was a failure point that we observed last year. And anyways, so that's that. It's still lighter. Okay, yeah, if there are any more questions, we can get those at the end, but we're going to hand it off to Jimmy and Propulsion. So thank you, everyone.
Okay, obligatory mic check. Can people hear me? All right, I'm not seeing anyone doing this, so I think we're good. All right, so propulsion, the fire and smoke. Let's get going. This was already spoiled, but the propulsion system, the big reveal. For those of you who are familiar with our systems, you'll note that this is last year's CAD model. The reason I'm putting it up here is to kind of orient the audience of what I'm talking about when I say different components. So we're a hybrid rocket, which means we use paraffin wax as our solid fuel and liquid nitrous oxide as our oxidizer. And those are stored separately before ignition with the oxidizer tank holding our oxidizer, which is then flowed through the actuated valve bay, which allows us to dictate exactly when we want to start flowing oxidizer and beginning our combustion process into the combustion chamber, which contains the thermal protection, the fuel, and a couple other systems. So without much further ado, let me get into the design requirements and start talking about what we're trying to achieve here with the propulsion system. So our total impulse is 9,200 pound-seconds. That's a requirement. That's the upper limit of what we can do at IREC. That's the top of the O-class motor. So we're limited to that by design of, where our design limit is imposed by competition. We could go higher if we wanted to. Similarly, we have to use non-toxic propellant as well as keep our pressure vessels at a factor safety of 2. Again, IREC requirements for both of those, as well as achieve a stability of 1.5 calibers of static margin off the rail, which is how IREC defines a stable rocket. To do that, in past years, we've needed a minimum peak thrust of 1,200 pounds. That's based on last year's weight. So if all the weight saving efforts that Austin and our team is trying to implement goes into effect, that number might come down a little bit. Alternatively, we could shorten the launch rail. We also ourselves have elected to impose a minimum factor safety of 1.5 across all parts. That's not our IREC requirement. That's just something that we're trying to achieve, although most of our parts in the load path are quite a bit higher than that. This is just for things where it's an extremely conservative estimate that we're trying to reach at least that 1.5. So some design goals, as always, and as every team's trying to achieve, we want to make things lighter while maintaining the same level of reliability and our factors of safety. But we have 2 new design goals for this year, which is that we want to have a subsonic trajectory, as well as we want to be able to use a composite overwrap pressure vessel, or COPV, which means we need to be compatible with both our normal aluminum oxidizer tank and that new composite oxidizer tank. I'll go a little bit more into how we're going to achieve these later slides. But first, kind of giving an overview of what the combustion chamber looks like and what the propulsion system is. Again, if you're familiar with our systems, this isn't very different. Most of what we've been doing on this side of the propulsion system is optimization and iteration on designs that have already been left. The last couple of years have given us some pretty good starting points to work from. So there's some areas there's not a lot that we have to change, which is good, but there are a couple things that we think we can improve. So I'll go over those. Combustion chamber has a lot going on in it. We start here at the injector bulkhead, which is where oxidizer is atomized and injected into the fuel grain, which is housed within the thermal protection, the precombustor, outer liner, and postcombustor, which protects the combustion chamber from melting, which is an important consideration, and then eventually ejected out through the nozzle as thrust. Some important factors and numbers to keep in mind for the combustion chamber. The total weight of this thing is 19 pounds, and then an additional 12 pounds of fuel was added in there, and this igniter to get it all started. Just a bit of rocket candy, which is something that we've had a lot of success in the past. We also have an overall factor, or we have a factor of safety of 3.3 on the aluminum combustion chamber, which is the outermost part here, although there are some other factors of safety inside on the other components that I'll get into later if you were to model them as a pressure vessel with no support. We assume a combustion chamber pressure of 500 psi for that calculation, although that is a worst case scenario, and we haven't actually really detected much more than a pressure spike at that level. Our thermal protection is a linen phenolic. That's something that we've selected and continue to use based on our flight heritage, although we are working on programs to get out of phenolic and into something that's a little bit cheaper, and I'll go into that in a couple slides. And finally, our L-star ranges are pretty similar to previous iterations. That's because we have had a lot of success with these values. And then until we get a little bit more time to go and model, to make a more thorough model of our motor, we don't really want to deviate much from this. So that was one of our design constraints. We want to keep our L-stars about the same as they were in previous years because that has had flight-proven success. Going through the high-level parameters of our motor, we are trying again to hit that 1,200 pounds of thrust, and we do that with 3 pounds per second of oxidizer flow and 1 pound per second of fuel, for a total of 4 pounds per second over a total burn time of 12 seconds, which is a bit of an increase in, over previous iterations. That does mean we're running at an oxidizer to fuel ratio of about 3, which is pretty fuel rich, but that's by design. We have shown better performance when we're running intentionally fuel rich, as well as it keeps our system from being exposed to the oxidizer directly. Some other figures of merit. Note that combustion chamber pressure has actually been is on average lower, or during the steady state burn, lower than that peak that we took the initial factor safety for, and that we have changed this area ratio. I'll go into why we did that, but that's probably the biggest change in the combustion chamber from previous years, is that area ratio got a little bit larger. So starting at the top of the combustion chamber, the injector. This is what starts the oxidizer flow into the combustion chamber. It's what gets it atomized, and it starts promoting some mixing of the fuel and oxidizer. This bulkhead also is the structural joining between the combustion chamber and the rest of the rocket, which is why it's so beefy, and allows for a lot of different sensors to start getting a pressure tapping into the combustion chamber, which is how we get that data. Going into details on those plates, because that's what's doing the actual injection. We have this injector plate, which is last year's design, and that's our baseline going into this year, which is a self-impinging injector. That's where the flows run into each other. That helps promote atomization and mixing. I should note that how we determine the quality of our injector plate designs is mostly empirical. We have a couple designs. I'll show a candidate replacement for this on the next slide. What we do is we run CO2 through it, which is a pretty accurate substitute for nitrous and not reactive, and a lot cheaper. So we run that through our ejection plates, observe the resulting plume, and basically come up with a qualitative judgment on which one's mixing better, which one's atomizing better. It's mostly an experimental process there. One of the designs that we are proposed instead of this direct fixed self-impinging holes is to do a series of 5 groups of 3 mutually impinging swirl type configuration, which we think might further promote atomization, as well as introduce some circulation going on into that injected plume, which may further promote mixing. Again, this has to be tested experimentally to see if it'll work, so we don't quite know what will happen here. But it's one of the ideas we're interested in trying. Going to the exact opposite end of the combustion chamber, the exit instead of the entrance, we have the nozzle, which is made out of graphite, which is, again, something that we've had a lot of history with and success using graphite nozzles, as they're somewhat ablative, but also pretty resistant to the high temperatures of our combustion. So I had mentioned that our biggest change is that we had decreased this throat area to get a higher area ratio. We did that because of some iterations on our motor modeling that when using CEA data, newer CEA data gave us slightly different chemical properties and suggested a different optimal area ratio. We also factored in for ambient conditions during launch at IREC, taking into account the pressure, taking into account the temperature as well as the pressure from altitude. And that all kind of came into this result. Although it's something that we're going to continue to analyze and make sure that we're confident in that change. I should also note that we have pretty much completely replaced the converging section with thermal protection, which is the next slide. We do this for a couple of reasons. The primary one is that that's the location that temperatures are the hottest in the nozzle, and it's also the location that's going to see the most ablation. So we intentionally replace this with thermal protection so that we can have something that is expendable each fire, and we're not having to replace the entire nozzle over the course of our testing cycle. Ideally, we would only make one nozzle for each year, and that's what we did last year, and it worked pretty well. We did make a couple changes to this converging section, mostly that we made the angle, the converging rate somewhat shallower to help increase the, help match the tangency of that angle and the nozzle. If you look really carefully at our assembled CAD, which will be in the next slide, you can notice that there's a slight angle discontinuity there, and we wanted to minimize that. However, we were also constrained by the fact that we have a lot of 1-inch thick phenolic stock, and we wanted to reuse it. So that's why we ended up with this result. Note that it's a pretty aggressive converging rate, but that's something that literature backs up isn't actually a significant concern, so we're keeping it as such a rapid convergence while we're keeping the divergence at a 15-degree half cone. Going to the thermal protection as a whole, you can kind of see right down here, if you're looking really carefully, that angle discontinuity, but it's hard to see on the full scale, on the projected screen. But going to our thermal protection as a whole, there's a couple other components other than that converging section. Notably the precombustor, the outer liner, and the postcombustor. And these combine to provide a region for fuel to continue to mix and burn, as well as just contain the hot combustion gases. It should be noted that we do seal this, our combustion chamber's heat shielding, with O-rings here and here, which does create a pressure vessel. So we have performed analysis, and we have that factor safety of 1.5, using the closer to the combustion pressure of 400 psi. Note, however, that this is a pretty conservative estimate because of the fact that this assumes no support from the combustion chamber on the heat shielding, which isn't true in actuality. We've intentionally made this decision because of the fact that we've noticed in previous years that our main failure mode for this heat shielding is gas paths, leaking out usually in the precombustor region and not due to pressure failure. So we've intentionally blocked that gas path and accepted the pressurization of the heat shielding. And it's something that has worked pretty well for us in previous iterations, so we're keeping with it. However, probably the biggest issue with our heat shielding is the fact that the precombustor is fairly expensive and time-consuming to manufacture. And part of that is due to the fact that it's made out of phenolic, which isn't a very cheap material. So one of the things we're looking into this year is replacing the phenolic in the precombustor with a different substance, in this case wood or wood composite. The reasoning behind that decision or that choice of research is that wood has similar ablative properties, especially certain composites of it, and some of them use phenolic resin to make the composite. So we believe that we can come up with a cheaper alternative and something that's a little bit easier to manufacture that can achieve the same results. So it's something that we have yet to design a test to actually compare the two. But it's something we'll be doing in the winters. We're making a precombustor out of phenolic and making one out of wood, and then basically subjecting them to the same conditions and comparing their ablative properties. We hope that this will help save time and money in the long run, as well as be more pleasant to manufacture. Moving into the core of that combustion chamber, the fuels, obviously what makes the rocket go. There's a lot going on in the fuels, but basically the purpose of the fuels is to provide that total impulse while not causing any detrimental instabilities, such as the fuel grain cracking and sloughing off, or other instabilities of it stuttering or going in and out. We use paraffin wax as our fuel, partially due to our long history and also due to its ease of how easy it is for us to manufacture it. And then we mix in various additives to the paraffin wax to create a fuel that has a higher regression rate and higher tensile strength. How we determine which additives to add is a bit of an experimental process, just like our injector. We have various additives that we've used in years past and that literature has suggested have the results we want to see. And we make a couple different compositions and test them in our subscale setup. One thing, though, I should point out before I go to some of those mixtures is that we're trying to implement vertical curing instead of a spin casting that we've done in the past, which is a bit of a step backwards to something SARP's had done originally and then moved to spin casting because of detrimental air bubbles. But we have a potential solution to the air bubbles in the vertical pour, and we have noticed in the past that spin forming has resulted in inhomogeneities within the fuel, which has meant that additives have separated to the outside when spun, and we'd like to remove that effect. So we're going to try pouring vertical and see which one is the most difficult to work with. We have a couple ideas we want to try out. So some of the fuel mixtures, there's quite a few of them and there's a lot of additives, so I'm not going to go into too much detail. If people have questions, feel free to ask. But essentially, all of these additives are being added to achieve one of two effects: increase the regression rate, which provides more thrust, or increase the hardness, which prevents instability. Some of these, this control composition is what we flew last year. This one up here is using smaller aluminum because we would have liked to use 3 micrometer aluminum, but we didn't have that on hand, and now we have a source. And then this is another one that we've had history with. And then what we're planning on doing is iterating slightly from each of these controls to see what the effects of adding each additive is. It's building on research that we've done in the past and trying to extend it forward. So moving outside of the rocket entirely, we've talked a lot about the fuel and what's inside the combustion chamber. How do things get inside the oxidizer tank? We do this pretty much completely remotely. We have a remote fill system that was developed largely last year and the year before that allows us to remotely load oxidizer and pressurize our tank without having any personnel on site, which is a great safety feature. We'd like to continue using the pneumatic ball valves that were so successful last year, but we'd also like to increase the line size and have a faster fill rate, because that was one of our probably biggest challenges in competition, was the fact that we couldn't fill within a half hour as we would have liked to. The fill procedure is fairly simple. We initially purge the tank with nitrogen to basically clear out any oxygen or anything else in there that could potentially react with the nitrous. Flow nitrous and try to fill the tank to our desired weight. For launch last year, that was 36 pounds, although the tank can hold up to 40. And then back pressurize with helium to achieve the desired tank pressure, which is 800 psi. For static fires where the rocket isn't going anywhere, we then immediately after the fire is finished, purge with CO2 to put out any fires that might be on or around the rocket or otherwise causing problems. This is basically a really in-depth diagram of our whole setup. I'm not going to go through it, but if you have questions, feel free to ask. The main change is the fact that we have a half-inch line going from the nitrous bottle all the way to the rocket and combining these two bottles. The other thing to notice is that we could potentially have 5 gas bottles set up at a time. But these are basically performing that operation I described to you earlier. During launch, obviously, we need to detach our fill line from the rocket. That's achieved doing using our fill arm, which was largely developed last year. This is the finished fill arm or detachment mechanism, and that's not changing significantly, except for the fact the line size is going up to a ½ inch. Otherwise, it's the same same scheme, which is to remotely detach the arm and separate from the rocket to allow it to fly free. So going into the big changes this year. The first is that we want to implement throttling, as Austin alluded to with talking about various tail cone designs. How we're going to do that is in the actuated valve bay. So the actuated valve controls the flow of oxidizer between the oxidizer tank and the combustion chamber, and it does that by a ball valve that is, for launch, rapidly opened by a vane actuator. That actuator happens in about 1/10 of a second, is to open the valve from full close to full open. But what we'd like to be able to do is partially close it again during flight to throttle down and decrease our mass flow. The reason for doing that is because of these charts that we've done here with our theoretical modeling. Assuming no changes in tail cone and just holding that constant and using our case from last year, we've noticed that if we throttle to about 40% of the thrust and hold the total impulse constant, we'll achieve an altitude gain of almost 2,000 feet. The reason for that is because the throttle trajectory stays subsonic, never going above that Mach of 1, which means it avoids a lot of the wave drag from heading through the sound barrier, which is a big potential saving in efficiency. Some more graphs kind of informing this analysis is basically what we assumed is we took last year's static fire data to get a thrust curve and assumed 2 seconds after ignition that we had started to systematically throttle down until for about 2.5 seconds to 40% of the thrust, and then kept this decay trend, but scaled 40% and kept the impulse constant. So there's a lot going into there, and this is what we input was the thrust curve. So a lot of these assumptions aren't fully solid, which we're going to have to test, and we're going to have to see what the properties are. But one thing to note is that we achieve the same stability as the unthrottled rockets. We're not losing anything there, and there's potential for a lot of altitude gain, so we're going to pursue it. How we're going to do that is pretty simple. We're going to add on a stepper motor to the same chain that is currently turning the vane actuator. Basically is when we go to ignite, the stepper motor will be unpowered and will be forced open by the vane actuator. And similarly, when we go to throttle, the vane actuator will be vented and can be closed by the stepper motor. The stepper motor will be closed quite a bit slower than the vane actuator opens, so that's something that will happen in flight, and we're already off the rails, so it's not as big of a concern. Obviously, this is something that's going to be subject to heavy testing to see if we actually get the performance we're anticipating, as well as what losses are present in the system, because when you have a valve that's partially closed, we're anticipating that we're going to see some pressure losses. We're just not sure what. So it's something that may or may not work out, but one of the advantages to this scheme is that if it turns out that throttling is not worth pursuing, the only thing we have to do to change back to last year's iteration is remove these 2 gears and shorten the chain. So it's pretty quick to move to an unthrottled flight. So we think that this is something that's worth pursuing because we're not really risking anything. A little bit more of a dramatic change is we'd like to change the oxidizer tank to have a hemispherical bulkhead, and this is because we're hoping to implement some weight savings from taking advantage of the fact that the interface requirements up here are pretty simple. It also has some similarities with the composite overwrap pressure vessel, which is something that we will, excuse me, it has some similarities with the COPV. So that is something that inspires us to try to implement dome geometry with the traditional ox tank to see if we can achieve that. The parameters of the ox tank has to satisfy is it has to hold up to 40 pounds of nitrous at up to 800 psi. Note that that's a derating of our ox tank from previous years. We used to rate them to 1,000 psi within a factor safety of 2 to 2,000 psi. We're still designing to 2,000 psi. We're just lowering the operating pressure because we never actually use 1,000 psi in the field. This will just make proof testing a little bit gentler on our systems. One thing to note is that while we have a curved bulkhead at the top, the requirements at the bottom are not so easy to work with a curved bulkhead. So we're going to keep a flat bulkhead at the bottom of the ox tank to aid with that integration with the actuated valve. Showing the completed assembly, you can see that one side's flat, one side's curved. And the factor of safety on this design is currently at 2.7, but those are just hand calculations. FEA is currently ongoing, but it's something that we haven't had a chance to work on. Also, this analysis suggests that we can decrease the thickness to 0.2 inches, and combining that with the bulkhead change potentially could be a 9-pound saving over last year's oxidizer tank, which is pretty dramatic. However, we need to complete our FEA to see if the welds are going to be able to hold up to that thickness decrease, and it's something that we're not entirely sure of, so this weight savings may come back a bit. Which leads me to something that Structures and Propulsion has been collaborating on, which is the composite overwrap pressure vessel that we've been alluding to. This is kind of the same mission as the oxidizer tank, which is to hold the nitrous and hold it. In this case, it's being designed for up to 2,400 psi because of the fact that IREC specifies any composite tanks must have a factor safety of 3. But because it's wrapped with carbon fiber, it represents potentially 55% weight savings over even the trimmed down design that I just showed you. So this potentially could be a huge weight savings for the rocket, which translates to a huge altitude gains without any need to increase impulse. How it's made is not too complicated. Basically, we make a traditional skin like we would, we make an aluminum skin like we'd make a traditional oxidizer tank, and then we wrap it with filament to provide that strength from the composite so that the skin's holding the oxidizer in, but the composite wrap is what's providing the strength. This, of course, will require access to tools that we don't have on campus. So we're hoping to get a sponsorship on to be able to use a filament winder. I'll go into details of what the COPV is going to be manufactured, which is first we have to make that skin, which requires spin forming it. It's something that a couple companies in the area have the capability to do, and we're in contact with them to see if they will sponsor us or at least see what their price is to do so. But because by spin forming, we can avoid using any welds to make the bulkheads and the tube. It'll be just a continuous part here, which will help reduce weight and make winding it easier, which is something that we hope to do with Sistema. We're in contact with them right now. One thing to note is that the fittings on the COPV would not fit into the thin metal of the skin, so they'll have to be welded on, which is something that we will have to make in-house and just attach with welding, again, professionally done, as Austin mentioned. Finally, it's hard to see here, but we will use the winder to wrap some extra thickness to make a ring around the COPV at both the aft and fore ends, right before the transition to the bulkhead, which will then be bonded directly to the main body tube, which will remove the the COPV from the load path, not because it can't hold the axial loading, our analysis shows that it can, but because we're concerned about unexpected buckling modes from the thin skin. So we decided that it wasn't worth putting it in the load path for the first year of flight. One thing to note is that because this tank is a completely new design challenge for us, it'll require methods like ultrasonic inspection that we don't have on site, but we're hoping that we could also get that through a company like Sistema if we're going to be able to get the access to their filament winder. That's something that'll have to be discussed in the next couple months. So it's on the horizon, but it's something we're excited for. Then really quickly, propulsion schedule is pretty long and detailed. The thing I want to point out is that we're pushing in a bit of an aggressive schedule to fit in potentially 4 static fires as well as a test flight. It's something that we're currently on track for, but if we do end up slipping our schedule of finishing manufacturing by mid-February, we have a lot of room to make it up by removing a static fire or removing a test flight. With that, I think I have a couple minutes for questions. Go for it, Trevor. Failure modes in the throttling valve. It's something that we're concerned of. You mean like it not closing all the way or closing too far? So closing too far is something we're concerned of, and we're going to have to come up with ways to. It's going to be a programmatic fix to make sure that it can't close too far. If it doesn't close enough, it's kind of a failure that won't hurt the mission. We'll lose altitude, but we're in no risk of losing the rocket. So it's something that we're willing to accept on that case, is that yes, it's possible that once the rocket's off the rail that we may not ever get this throttle signal, but we would lose no altitude, is the anticipation there. Sure. It is. So it's something that we're going to have to analyze really carefully, and we're going to do a lot of testing to see if it's possible for it to close. And basically, the current plan is to run an iteration of tests, like a battery of tests, test it basically 15, 20 times and see if it ever does close beyond where we told it to. We're going to have to do some more analysis to see why and if there's any way we can put a mechanical prevention. One thought is like potentially close it the opposite direction that it opened and put a hard stop. But it's something we have to work on. And then I guess I should repeat for the live stream. The question was, do we have any failure modes that we've considered for the throttling the ball valve? And that was my answer, was to some extent, but we're also working mostly on how we'd implement. Thought I saw another hand, but. Okay. All right, well, there'll be time for more questions at the end if you have any. Otherwise, I think it's time for avionics. You want it? In case. Top one.
Hi, everyone. Can you hear me back there? Awesome. Is that me, or is the other mic still on? Is it off now? No, it's me? Oh, weird. Here. Does that fix it? There you go. Hi, everyone. My name's Sabrina. I'm the avionics this year, and I was also the avionics lead last year, so I might be a familiar face to some of you. So these are the projects currently under the avionics name. The first two are more traditional avionics projects that have more to do with telemetry, but we've also taken over some other control systems and electronics on the rocket. And those two projects specifically, ignition and injection control and remote flow control, interface more with propulsion directly than any other team. So the first project up is network and communications. And this project really came out of the need for a very easy to use interface if we were to add more complexity and more computers into our system. So last year was the first year that we actually had a wireless system for all of our computers to interact with each other on. And this year we're expanding that. So last year we started with just a Wi-Fi bridge between ground control and the launch rail. This year we want to extend that network to include the rocket itself. So to create this continuous telemetry link between the rocket and ground control from 30,000 feet. So here is a diagram of what we hope for that to look like. You can see here on the left, we hope that in the future, if we need to add more microcontrollers on board of the rocket, that we can do so very easily by connecting it to this Ethernet switch. These microcontrollers can either be Raspberry Pis or Arduinos or really any other microcontroller, as long as it has access to Ethernet and can communicate over Ethernet. That switch will then communicate with a main communications computer. This year there'll be a Raspberry Pi, just because it has a lot of the inbuilt network functionalities that we're looking to use. And then between the Raspberry Pi and the antenna, there'll be a serial link in which the antenna will then transmit out and be collected with a Yagi antenna back at ground station that's connected to our main ground station computer. And this year that will be a Raspberry Pi, which is same to the system that we were using last year. So here's some of the hardware that we are looking to use. This right here is our Ethernet switch, and it currently has space for 8 computers. This year, we're not looking to use 8 computers, but we want to allow for growth in future systems. The radio that we're using is this one. We're looking to use the 900 band. And you can see here that it has space for 2 antennas. It's because this radio will choose between the 2 antennas depending on which one has the better signal to transmit on. We're choosing to use little rubber duck antennas for this onboard radio due to the space constraint. So the system will be located within the actuated valve bay. And to save on space, we're choosing to use these smaller antennas, and we're hoping by having 2, that's going to give us a better chance of getting the data back on the ground. So we're also planning to use a Yagi antenna to receive this on the ground. And then lastly, the thing that's included is a system that we were actually using last year, which worked really well and reliably, which was these Ubiquiti Light Beam MFi Wi-Fi bridges. So this next project is flight data, and its main point is to collect data that we can analyze in the future, so that we can see how well our design of the rocket performed. And then this system will also be collecting supplementary tracking data that will be transmitted back to ground, so that we can ideally use that data to actually find the rocket, which is kind of important. So we have a working prototype of our system right there to the left. We are using Arduino DUI this year. It is a higher speed, much more complex Arduino, but still a little simpler than a Raspberry Pi. So this is the type of data that we're looking to collect. We have IMU, GPS, and then pressure data from the oxidizer chamber and the combustion chamber. Those 3 are ones that we will be transmitting back to the ground station. The first one is so that we can analyze or not necessarily analyze, but so that we can actually see how the rocket is doing while we're in the air, because that's something we all kind of want to know. And then the second one, the GPS, is obviously to help assist finding the actual rocket. And the last one is to assist with fill procedures, which I'll talk about in a later project. There will be a few data points that are stored locally because we're interested in them and because we want to use it for future years, but not as important that we actually transmit it back to ground. So most of all, we want to make sure that we find the rocket. So we do actually have commercial off-the-shelf tracking beacons on board the rocket as well. We have an APRS unit, and then we'll also have 2 low-powered tracking beacons on board the rocket. And these worked reliably last year, and then also have a lifetime of 2 days with the batteries that they have. So in regards to testing, we have some different types of testing that we want to perform. The first type of testing is a subscale launch. So the idea is to put our avionics systems onto a smaller rocket, launch it and kind of see how it performs, and to also maybe test how our telemetry performs while it's in the air. Secondly, we plan to do vibrational testing. So in the civil engineering department, we actually have a vibrational table that they're willing to let us use. And luckily, we get to do that for free. And then so we're planning to do so in order to test the structural integrity of our housing. And then lastly, we plan to do temperature testing. Fix it. We plan to do temperature testing just to make sure that we can withstand the desert heat, which last year looked to be about 120 Fahrenheit. So I want to quickly talk about what our launch sequence looks like before I talk about our control schemes. The first thing that we do is we arm everything while we're still at the launch rail. So we arm the recovery systems. We also arm all the control systems. And that includes like checking all of our valves and some physical switches to make sure that our igniter doesn't go while we're anywhere near the rocket. After we leave the launch pad, we begin filling procedures. And then after fill procedure is done and we've reached our desired weight, we disconnect our fill line from the rocket, which is something that Jimmy had talked about during his section. And we get a go from all of the leads to make sure that we're all set and ready to go. And then we begin the ignition sequence. And that involves lighting the igniter. And we have a 2-second delay after the igniter before we actuate the valve that actually injects the oxidizer into the combustion chamber. Then we launch, and ideally after 2 seconds, we throttle down by actuating the stepper motor that Jimmy had talked about in propulsion. So the first control system that I will talk about is the ignition and injection control. So as I said, this is what's lighting the igniters and what's going to actuate the vane actuator as well as the stepper motor. This system is going to include Arduinos, both on the ground and on the rocket, because the 2 things that we're actually trying to do are in separate places. One is at the launch rail, and one is on the rocket itself. So all of these computers need to be able to communicate with each other and ground station. And so we've equipped each with a Ethernet shield. And then because of the things that we're actuating really means whether we're just providing power to them or not, we've also included some relay shields just to make it easier and more compact. So here's kind of a control flow diagram for this system, and it's really offering these main functionalities. The first is whether or not we can connect to it on the network, so can we actually communicate with it. The second thing that we're doing is checking the continuity of our igniters, because we want to make sure that all of our igniters are hooked up properly before we go to attempt to fire it. Third, we want to see the batteries and the voltage of the batteries to see whether or not maybe it's not fully charged, maybe we need to switch them out, maybe a LiPo is not holding charge. We then have the functions that actually have to do with firing the rocket. First one would be to arm it, so that's the software arm. And then we have fire to start the ignition sequence, and then we have an abort to force a cold flow if we have to. And that's just dumping the oxidizer tank through the combustion chamber without lighting the igniter. So here is the ignition computer, and I can go over this more in depth if anyone has questions on it. But the ignition computer, we've chosen between the 2 risks of accidental cold flow and accidental ignition, we've chosen accidental ignition as something we want to place more focus on, because we found that accidental cold flow wasn't as much of an issue, especially with last year's design moving over to a vane actuator to actuate that valve. So in this case, we have 2 Arduinos that are actually handling the ignition of, or sorry, the igniters, and then a physical switch and a couple of relays, and you can kind of see how we're planning to take the battery voltage and a continuity test over here. So this is the schematic for the injection computer. It is not including what we would be using to control the stepper motor for throttling. It's something that we're still developing. But there are a lot of similarities here to the other one. In this case, we only have 1 computer that is controlling this part of the sequence. But the same idea here for testing our battery voltage, and then this would be the relay schematic to actually actuate the solenoid. Lastly, I want to talk about remote fill control, which is a really important thing that we have, and we're always really proud of having this system because we like to say that we were doing this before anybody else was doing this remotely. But last year was the first year that we did it through wireless communication. We are going to continue to do that again this year. This system is one that's controlling the valves as well as the disconnection of the fill line. And it's going to be taking pressure data as well as weight data in order to assist with that. So because we're working with some pretty dangerous gases like nitrous, we want to make sure that we have a lot of built-in redundancies. So that is going to include some software and hardware devices to make sure that we don't have valves open when we don't want to, or valves closed when we don't necessarily want to. Then again, we always want to make sure that if things were to fail, they're failing in a safe manner. So the first thing that we do is we actually make sure that the valves themselves are set so they're naturally open, so that in the case that we lose power, then everything vents properly. We also want to make sure that we want to prevent certain valves from being opened at the same time. And if, let's say, our network were to drop at any point, we can actually see that and then trigger the safe mode to vent everything again. And lastly, in the way that we communicate these instruction packets between the control station and the launch rail, we retransmit our desired state of every single valve, so that in case some packet gets mangled, upon receiving the next one, it resolves itself. You can see here a diagram of what we would do to prevent like four bottles from being opened going into the fill line at the same time. We've kind of changed these switches are meant to represent relays, but we switch them to switches just to make things less cluttered. But the idea is that between these 4 valves, only one of them can be open at any time, and that's just a hardware redundancy. So here's the control flow that we plan to have if for both manual and autonomous fill. We are developing an autonomous system to fill this. So ideally, we press a button, step back, and it just kind of does its thing. But the idea is that we fill and we see, we look at the pressure differentials. If the pressure between the oxidizer tank and that of the bottle seem to equalize, then we vent the oxidizer tank to recreate that pressure difference. And we just continue this process until our targeted weight is reached. And then at that point, we would disconnect the lines, and then we'd move on to the actual ignition sequence. This is actually my last slide, so I am now open to questions if you guys have any. Questions? Yes. Yes. So the idea. Oh, so the question is whether the network that contains the telemetry link and the Wi-Fi bridge are on the same network. In a black box sense, yes. So we're working on an API to provide that functionality, so that if you're a computer on the rocket, then you can easily access a computer that is not on the rocket, that is through the Wi-Fi link. So the question is, do I know how powerful the radio is? And I don't, but Oliver does. So for the online viewers, it will be a 1-watt radio. So the network and flight data systems will both be placed in the actuated valve bay of the rocket. The question is where they were going to be. Yes. Mm-hmm. So the question is surrounding the actuated valve bay, if there's carbon, if that's going to be an issue for us. So that particular portion of the rocket was actually surrounded in fiberglass last year, which is RF permeable, which is what we plan to do again this year. So the question is whether or not we were considering heat and Raspberry Pis, because it seemed that teams last year did have an issue with that. We actually didn't personally find any issues with Raspberry Pis that we used last year. It is something that we're definitely always thinking about, and why we're planning to do some temperature testing with our system. But most of our stuff is also shrouded in things that are generally white. And I think that definitely helped us last year. I don't have concrete data until we do the temperature testing, but we seem to fare well last year in that regard. Okay. Why wouldn't we have found it with the off-the-shelf skin? So the question was whether or not, or how we plan to make the commercial off-the-shelf beacons easier to use. And I guess he's basing that on last year's experience. Just for some context, last year our rocket landed extremely close to base in a somewhat dangerous way even. So there wasn't as much time to test the full functionality of that system. Matt, do you have any comments regarding that? Can you repeat the question? So the APRs that will provide GPS data, and we have a beacon that can, or we have a radio that can actually unpack those so that we can directly walk into it as long as we have the last packet that was transmitted to us. In regards to testing this, we do plan to do more testing with the system again, just to verify its functionality, and that will be done at the same time that we do some of the more subscale testing. Mm-hmm.
The launch control architecture the cause of that never determined for the Arduino failure.
Right. So the question is that 2 years ago we had used Arduinos to actuate our main valve, and that actually caused a lot of problems. Last year we'd used a Raspberry Pi and it seemed reliable. This year we're switching back to the Arduino, so he's asking whether or not we foresee any problems with that. 2 years ago, the other thing that was going on is that we were running directly just 120V AC onto the rocket to run some rev valves, which is something that we thought maybe was interfering with the signals of the microcontrollers. Last year, we switched our systems entirely over to DC batteries, so it might be creating, or when we were running AC, it might have been creating EMF that was distorting signals from the Arduinos. This year, I don't necessarily foresee it being a large issue, but it's obviously something that we'll be testing extensively. Cool. And I think we can move on to to recovery with Aaron Goldvogel.
All right, testing, testing. Everyone hear me? Thumbs up in the back? Great, thumbs up in the back. So hello, my name is Aaron Goldvogel. I am this year's recovery lead. I'm going to try and move a little fast because we seem to be a little bit behind schedule, so away we go. So the three technical subteams that you've heard from so far have been mostly concerned with getting our beautiful rocket all the way up to its apogee at 30,000 feet altitude, and now it falls to me to get our rocket back down in one piece. So as mandated by the rules of our competition, we will be using a dual deploy parachute system, which means that at apogee, at the very top of our arc, we're going to pop the nose cone off of the rocket with a CO2 ejection system. It will stay tethered to the rocket, but that will allow the drogue parachute, a smaller parachute, to come out. That will control our rocket speed as it descends from 30,000 feet, hopefully, to 1,500 feet, at which point our main parachute will deploy, come out, and guide us gently down to the ground for our final touchdown. We're doing a lot of cool new stuff this year, so let's get right to it. So the star, of course, of our parachute system are the parachutes themselves, and last year's design was to use a toroidal geometry, which is shown in that picture to the right. This geometry is both what we've bought off the shelf and made ourselves previously, so we've got a lot of experience with it. It's pretty easy to manufacture. It's made out of those panels shown in purple, and we know how to size them pretty well to get the descent speed that we want. And those sizes and descent speeds are shown on the slide behind me that I probably shouldn't turn around and read. So those are our circular parachutes. They should be extremely reliable, and we've had a lot of luck with them in the past, so we're doing them again. And a little bit about the analysis. We use the formula on the right to calculate how large they should be given the air density of where we are launching, the altitude, as well as our desired fall speed. So those are all important things to know when figuring out how big our parachute should be. So the parachutes are the big flashy thing that we'll see when the parachute is recovering, but what is controlling all of the events, what tells the rocket when to eject the nose cone and when to deploy the main parachute, are these altimeters. By the rules, we have to use at least one commercial off-the-shelf altimeter, and we choose to use two. These are Raven 3 altimeters, which we've had a lot of luck with in the past. They measure the altitude using primarily barometric pressure, but also accelerometers as a backup. They will, when they detect apogee, as in the barometric pressure stops going down and starts going up, they will send signals to various pyro charges. They are set up to be connected to E-matches, which are wires with a little bit of pyrogen on the end. And when they are sent a current by the altimeter, they will spark a little bit, and hopefully they're right next to some black powder, which will spark a bit more and make something happen. They will be housed inside of a 3D printed enclosure, which is something that we've done the last couple of years. That enclosure will reside inside of the recovery coupler on the underside of the recovery coupler's bulkhead, where they will be nice and safe as well as exposed to barometric pressure so that they'll know how high we are. Moving on to the systems that are actually deployed by the altimeters, the nose cone ejection system is, well, you might ask, how are we going to get the nose cone off of the rocket? Because that's the first step that happens at apogee, or none of our parachutes come out. Well, what we do is we pressurize the entire upper body tube of the rocket with carbon dioxide, with CO2, which is stored in these cylinders. It's very similar to what we've done in previous years, but our innovation this year is to turn these cylinders sideways so that they take up less space vertically, and as well as as well as move them up to the payload coupler so that they are out of the way of other systems. This also has the added benefit of not having to worry about accidentally ejecting our parachutes when we eject the nose cone, which is something we've worried about in the past and just don't have to if the gas comes from the top of the tube instead of the bottom of the tube. Additionally, part of the reason we can make them sideways now is because we've calculated exactly how much force from these size of canisters is going to be put on the payload coupler to push it off, and we've determined that even with significantly smaller canisters, we will still have 1,000 pounds of force, which is more than enough to eject our nose cone. This is just a little better schematic look at what the CO2 system looks like. There is a black powder charge inside of that left piece, and when it detonates, it sends a plunger into the top of the CO2 canister to puncture the diaphragm and vent the CO2 into the upper body tube. Again, this is very similar to what we've done and bought off the shelf in previous years, and we can still use that as a backup, but we want to make our own this year. So that's how the nose cone is going to get off of the rocket, but the other deployment that has to happen is the main parachute has to get out. While the rocket is falling under drogue, the main parachute is still tethered inside the rocket, and that tether is under tension, and in order to let the drogue pull the main out of the rocket, we need to cut that tether. So this piece is called the parachute stage separator, and it is a device to cut a tether under tension. The way it works is that these rings provide an enormous amount of mechanical advantage, so this latch is held together by very little force. But when we remove the very little force that's holding it together, it immediately separates. The way we did this last year to remove that little force was to cut a string with nichrome wire, which was difficult to manufacture and really fiddly to deal with. This year, we're moving to an off-the-shelf pyrotechnic cutter, which will be able to cut our restraining line very quickly and easily. Uses the same E-match sort of setup that we're using with the CO2 system, and is just really cool because pyrotechnics. Like the CO2 system, this is triggered by the altimeters, and this will be triggered at 1,500 feet altitude, and will release our main parachute. So now we get into something that I'm really excited about, because I said that we're going to be using circular parachutes, but what we would like to do this year is replace that main circular parachute, the larger one, with a directional guided parachute, specifically one that is robotically, autonomously controlled. And we've named that project Ares for the, oh, I shouldn't try and remember what the acronym is without looking at it. But the idea is to be able to guide our rocket back down to a chosen landing zone instead of wherever it ends up. This means that and another great thing about our rocket is that it's about person weight, which means that we can use parachutes that are designed for about person weight. And whether or not we manufacture them ourselves or use commercial off-the-shelf ones, such as this Regalo design, or actually base jumpers reserve parachutes, are both very good candidates for exactly the sort of performance we're looking for. And some of that performance is shown here. But of course, it's robotically controlled, which means we need a robot to be able to pull the strings and act like a skydiver. So what we've come up with is this device. This device holds on its arms like this the static lines of the parachute, which are the ones that take almost all of the load, but don't move back and forth to steer it. And then with two stepper motors controlled by a microcontroller, it can pull the control lines, which are under much less force. And by having control over these lines, we can cause the parachute to bank and steer. And hopefully also flare up at the very end to have a very, very gentle landing. This means that we need to have electronics on board in this harness to be measuring things like altitude via barometric pressure and as well as GPS location, because it needs to be able to know where it is to steer home. Let's see, did I miss anything? It's going to be battery powered, and and it will also use a magnetometer to estimate its bearing, so that it can get a feel for how the wind is pushing it. And once it knows how the wind is pushing it, it'll know what direction to land in, so it lands into the wind, which is a little more gentle than landing with the wind. So this is what our proposed flight path looks like under our guided parachute. There is the first part of the flight, which involves just beelining it for home. When we get within a certain distance of home that we know we're going to make it there, we start spiraling down to bleed off our excess altitude until we get pretty close to the ground, at which point we go exactly to where we want to land, turn into the wind, and when we think we're about 10 feet-ish off of the ground, then we're going to flare up the parachute, basically pull up for anyone who flies planes, and sort of stall out right before we hit the ground, to hit the ground as gently as possible. Another possible flight mode that we are looking at is, well, what if the drogue parachute, the small circular parachute that deploys at apogee, what if that fails? What if it does deploy, but it shreds, and we start falling much faster than we expect to? Well, an option is to deploy the main parachute and begin our flight and just end up spiraling for a whole lot longer, which means that, and the advantage of deploying our main parachute early is that we can recover a failed drogues. So the force on the rocket will be much less if we deploy the main parachute going slower than if we let it fall further and get going even faster before we deploy the main. That is technically a little bit against the competition rules to deploy our main parachute above 1,500 feet altitude, and we're going to be working with the competition to hopefully be able to have this option as a fail-safe. However, it is definitely an experimental and sort of a stretch goal for this project. Finally, our rigging of how we're going to rope the parachutes and all of the other stuff to the rest of the rocket. Last year's system used this really, really cool rope that was really, really great because it was so light and strong, and really, really terrible because it didn't stretch at all, which means that it needs to have a lot of mitigating factors to lessen the shock of parachute opening and make the acceleration, the force on the rest of the rocket a little bit gentler. Last year, we used Z-folds with a lot of masking tape to do this, and we believe that that just wasn't enough shock mitigation because masking tape rips just too darn easy. So what we plan to do is to also introduce these U-bites, which will be held together with about 15-pound test nylon string, and those should take about 15 pounds to break. And if we have 30 of them all in a line, then it should be one after the other 15-pound impulses when the parachute deploys, instead of one really big one. So that is all shock mitigation in order to make sure that our parachute deployment is as gentle as possible on the rest of the rocket. Finally, testing. We want to do a few different tests that we've never done before, and the most exciting of them, at least I think so, is dropping the entire recovery system out of a plane. We want to do this as a full test of main parachute deployment, which means that we have to push it out of a plane from a little higher than 1,500 feet where we want our main to deploy. Another test that we are looking at is, oh wait, no, sorry, that's the one on this slide. There are definite safety concerns about where we can do this. We're in contact with various people experienced with skydiving and throwing things out of planes and people with planes, as well as airports, because generally skydiving happens pretty close to an airport, and we don't want our robot parachute contraption to accidentally interrupt flight paths. So at the moment, we have a prospective farm that we can drop things over, and we're looking for a larger and even safer location that we can drop it. We're also looking at mitigation factors for safety, such as if this thing comes down ballistic, adding a whistle so that it sounds really scary and people know to duck and cover, as well as posting signs and making sure that anyone who could possibly be in the area knows what we're doing and that they should be watching the sky. The manufacturing will happen primarily on campus, and which is something we're really proud of. And we're going to be using a couple of some really great facilities here for our various projects. Moving on, I'm just going to breeze right through this slide, but the moral of the story is that we're going to be doing a lot of tests. A big focus on recovery this year is making everything as reliable and well tested as possible. So we are doing a ton of tests, and they're going to be ongoing, and there will be a real headache to schedule, but we're working on it. And that is it for recovery. So if you have any questions, now is the time. Yes? Okay. So the question was about mounting the CO2 system very high up, and worried about that mount being robust enough to keep all the parts in one place. Basically, our plan is to make a very robust mount for it, and to make sure that we really have explored the forces that these cylinders and their mounts are going to be experiencing in flight, especially during the acceleration of launch. The cylinders are going to be cantilevered a little bit, so we need to make sure that we really know what sort of forces to expect, and that we have modeled them with finite element analysis and other analyses. We have not done that analysis just yet, and we've not nailed down what the mounting structure is going to look like just yet. We have sort of preliminary stuff, but that will be complete very soon. Yes? I'm sorry, please repeat a little louder. So the question is, how are we going to make sure that the shock of parachute opening doesn't translate all the way through to the motor? Is that correct? Oh, the motor's on the, oh, gosh, I thought you meant the rocket motor. The motor's on the of the robotic control system. Okay, yes. So I could go back to that diagram. So the main load path of the parachutes is through those cables to the side that look really beefy and chunky, and is translated directly down into the swivel. The only load that goes to the motors themselves is from the control lines. The control lines take much less of the weight of the parachute, about 10 pounds, and so they shouldn't break the motors. So the motors are only experiencing the loads from the control lines. They are not taking the full loads of the parachute. Anyone else? Online questions? Okay. The question from the live chat is why did the parachute ejection fail last year, and what is being done to mitigate it this year? The best answer we've got is we're not super sure. What happened last year is, or at least what we think happened last year, is that both main and drogue deployment happened simultaneously, significantly lower than either were supposed to, which led to a lot of forces on our parachutes, which then failed. That doesn't quite fit with how everything works, because the main parachute shouldn't be able to deploy if the drogue fails, which means that the drogue must have succeeded at least a little bit, and we're basically not sure, and that's part of why we want to do flight testing. We think that putting the CO2 system at the top of the tube should be a lot safer than previous, but we're not 100% sure, and we're doing our best. Yes. I believe they're stepper motors, but they are geared DC motors, and I'm wrong. Okay. We will have to come back to more recovery questions at the end. Thank you.
Sweet. Hey guys, my name is James Freese. Let me get to my slides here. So I am the payload lead for SARP this year. Thanks for sticking to the end. We're almost done. I promise we saved the best for last. So the payload this year, for this talk, I'm going to try and go a little bit fast because we're running a little bit behind schedule. But I'm going to just give a quick overview because it is a new payload this year and it's a really exciting project. And then I'll go through the 4 different sub-projects within payload, kind of describe each one of those, and then just briefly talk about testing. So the payload this year is what's known as a plasma actuator. And for those of you that don't know, a plasma actuator is an electronic flow control device. And it has a relatively low technology readiness level. It's a TRL of 4, which just means the concept has been proven and it's been tested in a laboratory environment. And it's mostly been tested on the leading edge of airfoils. So this was something that really interests us a little bit last year, so we started doing some research. And then this year we took it on as the main payload. There's about 20 undergraduates working on it this year, which is a big increase from about 6 last year. So the goal basically for the year is to validate this plasma actuator concept on the nose cone of a rocket in a relevant environment, i.e. in atmospheric pressures. The sub goals of that would be we want to be able to prove that we can produce a plasma during the coast phase of the rocket and that the plasma had some actual effect on the flow. So just real quickly, like how does a plasma actuator work? So essentially, here's a little diagram. So we have the 4 key components are a power supply, 2 electrodes, and a dielectric in between them. So if we're able to apply a high frequency, high voltage signal to these 2 electrodes, essentially we're able to break down the airflow over the electrodes and ionize the gas. With that ionized gas coupled with the electric field between these electrodes, we're able to impart a body force on the neutral air particles, and that creates a net momentum this way, and we can essentially control flow. So these pictures here are kind of like a before and after example on an airfoil. You can see all the turbulence and flow separation with the plasma actuator off. You can see how greatly it's changed with the plasma actuator on. So there hasn't been much research, like I mentioned, with nose cones, so we're really looking into that as well. So the first aspect of this system is the structural aspect. Like we got to hold everything together, right? So we have a team working on that, and the 3 criteria are we wanted to fit into a 3U CubeSat form factor. The cage also had to act as a Faraday cage, which means that it had to block out electromagnetic interference in the RF spectrum. We get a lot of RF interference from the plasma itself, and because our electronics are going to be so close, right on the nose cone, we needed to protect them from that EMI. And then finally, it needs to act as the ground for our electronics. So we decided on aluminum for the material. It's highly conductive, so it'll work well as a Faraday cage, and also work well for our ground. And it's strong. And then we'll have like a access door here to easily access our electronics. We'll have the power supply in here, as well as some controls electronics down below. And those will be held on shelves. And all the components will be manufactured in-house. It's a possibility we might do some outsourcing for the aluminum welding. That's kind of hard. So analysis of the structural aspects. So we basically chose the thickness of the aluminum case based off the EMI shielding requirements, as well as obviously structural requirements. We did some quick hand calculations, assuming a total weight of about 10 pounds and a total max acceleration of about 10 Gs, and found that doing these hand calculations, our stresses within the cage were well under the yield stress. But we're going to keep doing some FEA, hopefully completed by CDR, in order to support those claims. Integration-wise, we'll be integrating with the payload coupler. There'll be 4 corner supports that we'll use to screw in the cage itself. And that'll hold it rigidly in place on the payload coupler. And then, like I mentioned, they'll be integrating with the plasma electronics and controls teams, which I'll talk about here in a bit. Going into more depth onto the electronics, there's kind of 2 main aspects of the electronics that we spent a lot of time. There's the power supply, and then there's the electrodes. So way over here, but these 2 components here, which I'll talk about on this slide, are basically constitute our power supply, and then here are our electrodes, which really are where the plasma gets formed. But the 2 components that make up the power supply are, the first is EVS driver, which is a really cool circuit. If we have time, I can show you the circuit diagram, but essentially you can feed in a DC voltage, and it outputs a very high frequency AC. So we'll get from that about 15 kilohertz, which is within the operating range of the next component, which is a flyback transformer. And from there, we're able to step up about from 24 volts to anywhere between 3 and 8 kV, depending on how many windings we put on the transformer. So with those 2 things combined, we can convert a 24 volt DC battery pack signal, essentially go through this and output 15 kilohertz high voltage signal to these electrodes. And just a couple things back on this. So both of these components are pretty dang small, pretty lightweight, so we needed something that would be easily integrated into the nose cone. So this fit the bill for that. The electrode design is the next key aspect. We had to work closely with the nose cone team. As you can see here, there's going to be actually a small inset within the nose cone in which we're going to place our electrodes. But the main criteria were we wanted to make sure that the electrodes were flush to the nose cone. We didn't want to trip any flow prematurely. We wanted all the change in flow characteristics to be due to the plasma itself, and not any like physical like bumps on the nose cone. And then we also need to have this buried electrode, which is the aft electrode, needed to be under the dielectric. To talk a little bit more about the manufacturing, so the dielectric we went with, which is like modeled here, is this like quarter cylinder thing here. It's actually a ceramic is what we decided to go through, and that's going to be slip casted in the MSE department. We chose that based off its dielectric properties. And then the electrodes are going to be sputter coated here on campus. It's a really cool process. It's almost like spray painting of like a copper. And we can get a really, really thin copper electrode. That way we don't have any standoff from the nose cone. We don't trip any flow. And then we'll have some bolts, conductive bolts that will go through the ceramic and the electrodes. Those will help adhere the electrodes to the nose cone, as well as aid in conductive pathways. That's how we're going to get the signal to the electrodes themselves. Just quickly, the integration. So we work with the nose cone, like I mentioned. We want to make sure that the insets here that get added to the fiberglass layup fit perfectly with our ceramics. We want to minimize the amount of holes that end up going into the nose cone. We don't want to turn it into Swiss cheese. And then we need to ensure that the temperature, this was mentioned earlier, but ensure that the temperature through the plasma will stay within the operating temperatures of the fiberglass. So we'll do some tests for that. We also sort of integrate, we affect the avionics team. Because like I mentioned, we have the EMI. You can hear the avionics guys laughing. We have a lot of EMI. And that doesn't work well with like the avionics electronics, especially because they're trying to send and receive signals. So they can't necessarily put their electronics in a Faraday cage like we can. So the solution to that is basically we need to move the avionics electronics as far aft and away from our EMI source as possible. You can see here in this plot that the electric and magnetic fields fall off as 1 over r squared. So as we get further and further away, we're going to lose magnitude quite quickly. And then we also need to do some tests. We want to operate at the minimum voltage that we can in order to produce plasma. This graph kind of shows there's a linear relationship with operating voltage and the electric field strength. So if we can minimize that, we can minimize electric field strength and make everybody happy. Did I skip a slide? Yeah. Okay, so going on to the diagnostic side of things, this is how we're really going to be able to tell what effect the plasma had on the flow. So we want to be able to quantify that effect. So we decided to choose heat flux sensors to do that, mainly because they're relatively cheap, had a really high fidelity, measurement fidelity, and were like flat to the nose cone. They minimally disrupted the flow. We're able to get 2 quantities out of these heat flux sensors, the heat flux and the change in temperature. And from that, we can get the heat transfer coefficient. And you can kind of look at this plot down here, but you can see that the difference between laminar and turbulent heat flux coefficient is like quite large. So it's going to be hard to like actually like quantify like how much turbulent flow there was, but at least we'll be able to say like, okay, we were actually able to delay turbulent flow, and instead of it being turbulent like it used to be, it's now laminar. So that's a success in our book. This is kind of a little bit more about the heat flux sensor. We were originally going to go with piezoelectric pressure sensors, but they didn't have the high enough fidelity to really measure the differences between what was going to be happening between laminar and turbulent flow. We're going to be doing some CFD. We've already started it, and some wind tunnel tests coming up actually next week to determine also like the best place for these sensors where they're going to be located on the nose cone. One other benefit to these is that they're really easy to integrate with the Arduinos that are in our control system, which is what I'll talk about next. So the diagnostic team integrates with the controls team, and the controls are in charge. Really, the diagnostics are the sensors for the Arduinos, and the Arduinos are the controls team. So talking a little bit more about them, their design criteria is threefold. First, they need to be able to detect when the rocket enters into that coast phase. At that point, they're going to send a signal to an electronic relay, and that will turn our circuit on and help us create plasma. And then after a set amount of time, then we'll turn that circuit off. And then the last thing is it's going to be logging the data that we're getting out from those sensors from the diagnostic team. Here's kind of a little schematic, and I'll talk about that next. So the main control algorithms that we'll be using is something that's never really been done on our rocket before, but it's called in-flight error checking. And so with that comes, we'll be using like an array of altimeters. And so they'll constantly be comparing their signals to each other. And the Arduino primary controller will be using the differences in error to determine like the best time to turn on when we've entered that coast phase. It's a challenge that the controls team kind of wanted to take on. They're like, nah, we don't want to just use one altimeter, let's use 4. So we're like, all right, let's go for it, that's awesome. So that'll be running on the primary controller, which will also be powering the electronics and reading in the inputs from the diagnostics team. The primary controller will be talking to a secondary controller, and that will be in charge of storing all of the data that we're getting from the diagnostics team locally on board on an SD card. So I mentioned that the controls team needs to read and log heat flux sensor data. They also need to log some voltage data from the electronics team. You're going to be working with the electronics team furthermore to activate that relay. And then there's a possibility that the nose cone team, as mentioned before, will be adding a pitot tube to the nose cone. So we've offered to help them out, and we'll be reading in their data too and storing that locally on our controller. So testing-wise, I'll just like briefly mention some of these. So the first test we'll probably do is after the support cage gets created, we're going to do some Faraday cage testing. Does it in fact block out the EMI? We'll do some plasma formation testing once we get the circuits made. And then once we get plasma formed, then we'll be going into the next 2 bullet points, which are the heat transfer testing with the nose cone team, and then the avionics EMI testing. We want to make sure that at the distances that they're set at, we're going to not get any interference. Then this one's pretty cool. The controls team is going to basically strap their controller onto like a drone and then send it through like a bunch of different varying accelerations and altitudes and see if they get the expected behavior out of their system. And then these last 2 are once we incorporate all of these systems together, we're going to be doing some vibrational testing. And then once implemented into the nose cone, hopefully we can do some wind tunnel testing and be able to analyze on the ground how this plasma affects the flow. Here's a kind of a bridged schedule. Basically for the remainder of the year, a lot of it is going to be focused on testing because this is a new project. We want to really test the heck out of it before launching. So we'll be doing that from the beginning of next quarter through the middle of spring quarter. That's it from me. Do you guys have any questions on the payload? Yeah, Oliver. Right. Yeah, so we have thought about that. Oh yeah. So the question from Oliver was for the pitot tube and the heat flux sensors, those are necessarily going to be outside of the Faraday cage. How are we going to protect them from the EMI? So that's something that we're still working on, and the first main way of combating that is just to protect the signal wires in like a mesh conductive material, and that can keep out any interference along the wires. And we're looking into ways of minimizing the actual interference on like the very surface of those heat flux sensors. But the majority of like any area in which it can be affected is going to be shielded. Yeah. So I'm not in charge of the altimeters, and my lead who's in charge of it isn't either, but I think what we were actually planning on using is like the IMU within the altimeters that we were getting, and looking at when the engine actually shuts off, as opposed to altitude pressure measurement. Oh yeah, online questions. Yeah. Sure. The question, I think, is how we determined the thickness of the Faraday cage, is what I'm assuming, and how we got values for the electric field. So I guess I can go back to this, and then I guess we'll start here. So this is for choosing the thickness, this is a plot of the frequency of the, so like we're in the RF range, which is going to be in the kilohertz all the way up to gigahertz range. But so we're above about 10 kilohertz to the right. And then this is our thickness of the Faraday cage material. This is something we found in a published paper. Essentially, our minimum actually is about 1 millimeter. We decided for a factor of safety as well as like considering structural loads. We decided to go with 1/8 of an inch, which is like 3 and a little bit above 3 millimeters. So we should be totally fine with the thickness there. And then she asked about the electric field strength. So basically, we figured that out, and we want to do some tests of our own. But it's been a lot of research because this is a new project. It's very R&D heavy. So these are plots from papers that we found where they did studies with this exact same thing, plasma actuators, and they did electric and magnetic field strength measurements as a function of distance and as a function of applied voltage. So we got our expected electric and magnetic fields from published papers. We want to do some tests. Well, we will do some tests, though. Okay, so the question was regarding the heat flux sensors. Were those measurements at a single position at a single point in time, or were they spatially and temporally dependent, I guess? So there will be 4 heat flux sensors on the nose cone. There'll be 4 of the plasma actuator and 2 after that plasma actuator. We have 2 just basically for redundancy. And so to answer the spatial part, there'll be 4 different locations. And then they'll be measured as a function of time. So we'll have a change in temperature out of this thermocouple, and then a change in heat flux as a function of time. Mm-hmm. We still have the safe testing box, and we've updated our SOP to be safer. So we're going to add an interlock system as well as like a manual switch. And then there's a whole bunch of like personal protective equipment that we've added. And we're going to try and have a professor or somebody who's very well versed in high voltage electronics be present at all of our testing, because safety is our highest priority. So the question was, will the electric field strength be dependent on the ambient atmospheric conditions? And my short answer is I'm not entirely sure, but I can give a best guess, and that would be yes. First and foremost, it is dependent because the plasma is dependent on the atmospheric conditions. So if we don't have any plasma being made, we have no EMI. So I guess that's kind of a sneaky way of answering the question. But I would also assume that the electric field strength is probably dependent on a bunch of things within the atmosphere, i.e. probably pressure, and then also like the amount of like particles in the air that can be used as like points of breakdown, if that makes sense, or like water content as well. There's probably a bunch of things. So I mean, it'll all be figured out through testing, hopefully, because this is like a laboratory setup for sure. Okay, thanks, guys.
All right. Thanks, everyone, for coming and sticking through all this thing. I know it was a little bit long. We'll open it up for more questions that we didn't get to in a second here. Real quick, I do want to acknowledge everyone who made where we're at now happen, and everyone who will be helping us get to our final launch. Everyone on team, especially our project leads, they put in a lot of time getting us ready for this PDR and all that. All of the UW support, lots of professors, and many hands everywhere helping out. A bunch of other SARP friends who are not even UW related, they just like rockets. And then real quick, the biggest person I think to thank right now is Ben for running our live stream. If we could just give him a hand, that'd be cool. I kept seeing him sitting over there like waving his arms around and things were working and stuff. So I think he got it to work pretty well. So with that, do we have any other questions that we had to skip through? Cool. I think for our live stream questions we had, we'll just do those offline so we don't have to keep you guys all sitting here since we are over 8:30. So I think that's all we got. Thank you again for coming. We'll see you at CDR.